Engineers generally deal with effective values when designing equipment for alternating current systems. Effective values represent the equivalent heating effect of an alternating current or voltage compared to direct current value. They are typically used for practical calculations and measurements. Maximum values represent the peak values of alternating current waveforms, which can be significantly higher than the effective values. In the case of the example provided, equipment is rated for 277 volts per 480 volts. The effective value of 480 volts is 480 volts. The maximum value of 480 volts is 678.92 volts, which is approximately 1.4 times higher than the effective value. Engineers would typically consider the maximum voltage value when designing the equipment to ensure it can withstand potential voltage spikes and surges. This may involve using components with higher insulation ratings, thicker conductors, or surge protection devices. However, it is important to note that the equipment's continuous operation and performance are based on effective values. For instance, the equipment's power rating, efficiency, and temperature rise are determined using effective values. In summary, while maximum values are important for ensuring equipment durability, engineers primarily use effective values for most practical calculations and design considerations. Now, let's delve deeper into the concept of effective values, also known as root mean square or RMS values, and maximum values in alternating current circuits. In an alternating current system, voltage and current constantly change direction and magnitude over time, typically following a sinusoidal waveform. This means that at any given instant, the voltage or current can be at any point between its maximum positive value and its maximum negative value. Because these values are constantly changing, it's not practical to use instantaneous values for most calculations. Instead, we use the effective value, which represents the equivalent direct current value that would produce the same amount of heat in a resistive load. The relationship between effective and maximum values for a sinusoidal waveform is defined as follows. Effective value equals 0.707 times the maximum value. Conversely, maximum value equals effective value divided by 0.707. For example, if an alternating current has a maximum value of 14.14 amps, its effective value would be 10 amps because 14.14 times 0.707 equals 10. This means that a 14.14 amp alternating current would produce the same amount of heat in a resistor as a 10 amp direct current. Now, let's consider the implications of these different values on equipment design. As mentioned earlier, equipment is often rated for a specific voltage, such as 277 volts per 480 volts. This rating refers to the effective voltage that the equipment is designed to handle continuously. However, the actual voltage in the circuit will vary over time, reaching a maximum value that is higher than the effective value. For example, if a piece of equipment is rated for 480 volts, the maximum voltage in the circuit could be as high as 678.92 volts. It is important for engineers to consider this maximum voltage when designing the equipment, as it can have a significant impact on the performance and reliability of the equipment. One of the key concerns is insulation breakdown. If the voltage in the circuit exceeds the insulation rating of the equipment, it can cause a short circuit or other type of failure. Therefore, engineers must choose components with insulation ratings that are high enough to withstand the maximum voltage in the circuit. Another concern is surge protection. Voltage spikes and surges can occur in alternating current systems due to various factors, such as lightning strikes or switching operations. These surges can be much higher than the normal maximum voltage in the circuit and can damage or destroy equipment if it is not properly protected. Therefore, engineers often incorporate surge protection devices into their designs to protect equipment from these types of events. In addition to insulation and surge protection, engineers must also consider the impact of maximum voltage on other aspects of equipment design, such as conductor sizing and component selection. For example, thicker conductors may be required to handle the higher currents associated with maximum voltage, and components with higher voltage ratings may be needed to ensure reliable operation. However, It is also important to remember that the equipment's continuous operation and performance are based on effective values. The equipment's power rating, efficiency, and temperature rise are all determined using effective values, not maximum values. Therefore, engineers must strike a balance between designing for maximum voltage to ensure durability and designing for effective values to ensure optimal performance. Now, let's consider some specific examples of how engineers deal with maximum values in the design of different types of equipment. In the case of generators, engineers must consider the following factors. Firstly, increase in excitation. Will the exciter voltage be sufficient to produce the required excitation at full load or at a practical load of low power factor? Will the fields overheat at the increased excitation required? Secondly, increase in core loss. Will the iron overheat? Thirdly, decrease in armature copper loss for the same kilovolt ampere output. Will this offset the additional field and core loss? In the case of transformers, engineers must consider the following factors. Firstly, insulation. The insulation of the transformer must be able to withstand the maximum voltage in the circuit, as well as any voltage surges that may occur. Secondly, core saturation. The core of the transformer must be designed to avoid saturation at the maximum voltage, which can lead to increased losses and reduced efficiency. Thirdly, voltage regulation. The transformer must be designed to maintain a stable output voltage even when the input voltage varies. In the case of motors, engineers must consider the following factors. Firstly, insulation. The insulation of the motor windings must be able to withstand the maximum voltage in the circuit, as well as any voltage surges that may occur. Secondly, torque. The motor must be able to produce sufficient torque to start and operate the load at the maximum voltage. Thirdly, speed. The motor's speed must be controlled to prevent overspeeding at the maximum voltage. In addition to these specific examples, engineers also use various other techniques to deal with maximum values in equipment design. These include using computer simulations to model the behavior of equipment under different voltage conditions, conducting laboratory tests to verify the performance of equipment at maximum voltage, and implementing quality control procedures to ensure that equipment is manufactured to meet the required specifications. Now, let's discuss the concept of root mean square, or RMS, values in more detail. The RMS value of an alternating current or voltage is a way of representing its effective value. It is calculated by taking the square root of the mean, or average, of the squares of the instantaneous values of the current or voltage over one complete cycle. Mathematically, the RMS value can be expressed as follows. Root mean square equals the square root of 1 over t, integrated from 0 to t, of f of t squared, dt, where t is the period of the waveform and f of t is the instantaneous value of the current or voltage at time t. For a sinusoidal waveform, the RMS value is equal to the maximum value divided by the square root of 2, which is approximately equal to 0.707 times the maximum value. The RMS value is important because it represents the equivalent direct current value that would produce the same amount of heat in a resistive load. This means that the RMS value can be used to calculate the power dissipated in a circuit, as well as the voltage drop across a resistor. For example, if a resistor has an RMS current of 10 amps flowing through it, and the resistance is 5 ohms, then the power dissipated in the resistor is equal to I squared times R, which is 10 squared times 5, which equals 500 watts. Similarly, the voltage drop across the resistor is equal to I times R, which is 10 times 5, which equals 50 volts. It is important to note that the RMS value is not the same as the average value of an alternating current or voltage. The average value of a sinusoidal waveform over one complete cycle is 0 because the positive and negative halves of the waveform cancel each other out. However, the RMS value is always positive because it is calculated by squaring the instantaneous values of the current or voltage. In summary, the RMS value is a way of representing the effective value of an alternating current or voltage. It is calculated by taking the square root of the mean of the squares of the instantaneous values of the current or voltage over one complete cycle. The RMS value is important because it represents the equivalent direct current value that would produce the same amount of heat in a resistive load. Now, let's consider some practical examples of how engineers use RMS values in their work. When designing electrical circuits, engineers use RMS values to calculate the power dissipated in resistors, the voltage drop across components, and the overall efficiency of the circuit. When selecting components for electrical equipment, engineers use RMS values to ensure that the components are able to handle the expected current and voltage levels. When measuring the performance of electrical equipment, engineers use RMS values to determine the equipment's power output, efficiency, and other key parameters. When troubleshooting electrical problems, engineers use RMS values to identify faulty components and diagnose circuit problems. In addition to these practical examples, RMS values are also used in various theoretical calculations and analyses in electrical engineering. For example, RMS values are used to calculate the impedance of alternating current circuits, the power factor of alternating current loads, and the efficiency of alternating current machines. In conclusion, RMS values are an essential tool for electrical engineers. They are used in a wide range of practical applications and theoretical calculations to design, analyze, and troubleshoot electrical systems. Now let's delve into the National Electrical Code, or NEC, and how it relates to effective and maximum voltage values. The NEC is a set of standards for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC contains numerous provisions that relate to voltage levels, including requirements for insulation ratings, overcurrent protection, and grounding. One of the key requirements in the NEC is that electrical equipment must be rated for the voltage at which it is intended to be used. This rating refers to the effective voltage, or RMS voltage, of the circuit. For example, if a piece of equipment is rated for 480 volts, it must be suitable for use in a circuit with an RMS voltage of 480 volts. However, the NEC also recognizes that the actual voltage in an alternating current circuit will vary over time, reaching a maximum value that is higher than the effective value. Therefore, the NEC includes provisions to ensure that electrical equipment is protected from overvoltage conditions. One of these provisions is the requirement for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in a circuit if the current exceeds a certain level. This helps to protect electrical equipment from damage caused by overloads and short circuits. Another provision in the NEC is the requirement for grounding. Grounding is the process of connecting electrical equipment to the earth. This helps to prevent electric shock and reduce the risk of fire. The NEC also includes specific requirements for the grounding of electrical systems, including the size and type of grounding conductors. In addition to these general requirements, the NEC also includes specific requirements for different types of electrical equipment and installations. For example, the NEC includes specific requirements for the installation of transformers, motors, and generators. These requirements are designed to ensure that these types of equipment are installed safely and operate reliably. Now let's consider some specific examples of how the NEC relates to effective and maximum voltage values. Article 220 of the NEC covers branch circuit, feeder, and service calculations. This article provides guidance on how to calculate the load on an electrical circuit, which is necessary for determining the appropriate size of conductors and overcurrent protection devices. The calculations in Article 220 are based on the effective voltage of the circuit. Article 310 of the NEC covers conductors for general wiring. This article includes tables that specify the ampacity of different types of conductors, which is the maximum amount of current that a conductor can safely carry. The ampacity of a conductor is based on its insulation rating, its size, and the ambient temperature. The ampacity values in Article 310 are based on the effective voltage of the circuit. Article 430 of the NEC covers motors, motor circuits, and controllers. This article includes requirements for the protection of motors from overloads and short circuits. The overcurrent protection requirements in Article 430 are based on the effective voltage of the motor circuit. In summary, the NEC is a comprehensive set of standards for the safe installation of electrical wiring and equipment. It includes numerous provisions that relate to voltage levels, including requirements for insulation ratings, overcurrent protection, and grounding. The NEC is based on the effective voltage of electrical circuits, but it also recognizes that the actual voltage will vary over time, reaching a maximum value that is higher than the effective value. Therefore, the NEC includes provisions to ensure that electrical equipment is protected from overvoltage conditions. Now, let's discuss some additional considerations related to effective and maximum voltage values. One important consideration is the power factor of an alternating current circuit. The power factor is a measure of how efficiently electrical power is being used in the circuit. A power factor of 1 indicates that all of the electrical power is being used to do work, while a power factor of less than 1 indicates that some of the electrical power is being wasted. The power factor is affected by the presence of reactive loads such as inductors and capacitors in the circuit. Reactive loads cause the current and voltage waveforms to be out of phase with each other, which reduces the power factor. A low power factor can lead to increased energy costs, reduced equipment capacity, and voltage problems. Therefore, it is important to maintain a high power factor in alternating current circuits. Another important consideration is the presence of harmonics in alternating current circuits. Harmonics are unwanted frequencies that are multiples of the fundamental frequency of the alternating current waveform. Harmonics can be caused by nonlinear loads, such as electronic devices and arc furnaces. Harmonics can cause a variety of problems, including increased energy costs, equipment overheating, and communication interference. Therefore, it is important to mitigate harmonics in alternating current circuits. One way to mitigate harmonics is to use harmonic filters. Harmonic filters are devices that are designed to block or reduce the flow of harmonic currents. Harmonic filters can be installed at the source of the harmonics or at the point of use. Another way to mitigate harmonics is to use harmonic mitigating equipment. Harmonic mitigating equipment is designed to reduce the amount of harmonics generated by nonlinear loads. This type of equipment can be installed as part of the nonlinear load or as a separate device. In addition to power factor and harmonics, there are other factors that can affect voltage levels in alternating current circuits. These include voltage drops due to long conductor runs, voltage sags due to sudden increases in load, and voltage swells due to sudden decreases in load. Voltage drops can be mitigated by using larger conductors or by installing voltage regulators. Voltage sags and swells can be mitigated by using voltage regulators or by installing uninterruptible power supplies, or UPSs. In conclusion, effective and maximum voltage values are important considerations in the design, installation, and operation of electrical systems. Engineers must consider both effective and maximum voltage values to ensure that equipment is protected from overvoltage conditions and that electrical systems operate efficiently and reliably. Power factor, harmonics, and other factors can affect voltage levels in alternating current circuits and should be carefully monitored and mitigated.